Hello everyone, I am Dipayan, working as an associate lead data scientist in Sigmoid. In this series of tech talks, we are going to talk about sequential models. Let us get started. So what are sequence models? In simple explanation, sequence models are deep learning models to deal with sequence data. Now in sequence data points have some meaningful order. Data point at timestamp t has some relationship or dependency with data point at timestamp t-1. A variety of examples such as textual stream, audio clips, time series data comes under the spectrum of sequence data. Now, traditional machine learning or deep learning frameworks cannot handle this sequential data well. If we want to perform stock price prediction or the next word prediction for a given sequence of texts, sequential models can be used. Sequential models can be broadly classified into three types: one-to-many, where input data is of non-sequence type and output is of sequence type. For example, image captioning is a one-to-many sequence model where we provide an image and model captions that image. Then many-to-many, where input data is of sequence type and output is of non-sequence type. Next word prediction is an example of this type. And many-to-many, where input is of sequence type and output is also of sequence type. Machine translation, named entity recognition are the examples of this type. Now, there are plenty of use cases where sequence models are used. In speech recognition, an audio signal is converted into embedded vector form and provided to the model. Model outputs the text transcript. In video activity recognition, model needs to recognize the activity in a given video, which is nothing but a series of frames. In sentiment classification, model determines the polarity of a sentence, whether it's a positive sentence or a negative sentence. Now let us understand why sequence information is so much important by taking an example. Imagine you are reading a piece of text. Do you understand the words separately as different entities, or are you getting any information from this bunch of texts or this bunch of texts? Answer is no. But you understand the whole text when the words are ordered in meaningful manner, like this and this. So this kind of sequence information cannot be processed in normal machine learning or deep learning models. We need a way to pass previous time steps information to the next time step. Recurrent neural networks were built to fulfill that purpose only. We are going to talk about recurrent neural networks in the next part. In the last session, we have talked about sequence data. We have discussed that recurrent neural networks were built to handle sequence data. Now we will discuss about basics of recurrent neural networks. Recurrent neural network or RNNs are special type of neural networks to perform sequence data task. Let us think of a neural network as a black box with input unit and an output unit. So what RNN does? RNN adds a loop on top of that to convey information to the next steps. So we can imagine RNN as multiple copies of same network, each passing information to the next unit. For example, if we have this sequence of texts yellow is her favorite. Then we pass yellow at first in the model, and some information from that timestamp is passed to the next timestamp where is provided. In same fashion, information will be passed to the next unit till all the words are given to the model. And finally, when whole sequence is passed, the model will give the output as color. So now we will see the internals of a single RNN unit. Each RNN block has two major output components. One is hidden state, another one is output unit. Hidden state is the one responsible for passing current time steps information to the next timestamp. Now, output unit yields output at each timestamp as per requirement. This is mostly required where model is supposed to output a sequence at each timestamp. So, hidden state is a function of input unit and hidden state from the previous timestamp, and output unit is a function of hidden state. Now these functions can be tanh, sigmoid, etc. There are parameters which are associated with the input unit, hidden unit, and output unit, like U, V, W in the image. These are the parameters which are learned over time. Now, we can have different RNN architectures based on our requirement. For next word prediction kind of problem, we block the outputs at each stage except the last unit. In word-word mapping kind of problem, we have output from each timestamps. Now, in most of the tasks nowadays, we use encoder-decoder architecture. In encoder, we have RNN units where outputs are blocked. And in decoder, we have RNN units where we do not have inputs as such, but we have all the RNNs to give outputs at each timestamps. So suppose we have a sequence, we give that sequence to the encoder unit. Encoder makes it a single vector, single embedded vector. That embedded vector is passed to the decoder, and decoder gives output at each timestamp. We are going to talk about RNN learnings in the next part. In the last session, we have talked about RNN basics. Now we will talk about RNN learnings and some of the problems in RNN. When input data is provided at timestamp 0, state output units are calculated at 0 timestamp. Then some information is passed to timestamp 1 along with the data at timestamp 1. And output units are also calculated at 1 timestamp. Same process is repeated for the whole sequence. Now, once all the timestamps are completed, then calculated outputs are compared with the target outputs. So for example, in the given diagram, the correct output for the sequence is color, but the model has calculated that as song. By comparing the actual output with predicted output, errors are calculated. Then error gradients are generated. Finally, parameters of the models are updated using the gradients. Now, gradients are nothing but derivative terms with respect to model parameters. One important thing to notice is gradient at current timestamp consists of terms from past timestamps as well. For example, error gradient with respect to V at last timestamp consists of components from 0, 1 and second timestamp as well. Now this whole process of learning is called backpropagation with time. Calculation of gradients by multiplying the components over time leads to a large multiplicative term. Now let us look at two major shortcomings of RNNs. We have seen that RNN blocks contain activation functions such as sigmoid, tanh, etc., which are bounded by small intervals. That means corresponding gradients have very small values. These small values multiplied continuously make the resultant product very close to 0. This is called vanishing gradient problem. Because of this, the model does not learn very well. Also, long-term dependencies are not kept well in RNN. Suppose we have this sentence: the cat which was sitting on the road saw the dog and it ran away. If we want our model to identify which animal it is referring to, RNN will not do well here, since here are multiple words sitting between cat and it. Advanced sequence models such as LSTMs, GRUs deal with long-term dependencies and vanishing gradient problems well. So that's all regarding sequence model basics and RNNs. Let us get started. So in our Recurrent Neural Network Tech Talk, we have discussed how past timestamps information is propagated through time in RNNs. We have also seen that RNNs cannot handle long-term dependencies well. LSTM was developed mainly to address vanishing gradient problem and that long-term dependency. Now, LSTM and RNN blocks are fairly similar. Only difference is that LSTM uses cell state, forget get, remember get, etc. to overcome the challenges of RNNs. Mathematical functions such as tanh, sigmoid, etc. are used to incorporate these components. We will look into these components in more detail now. So forget get. Forget get takes current timestamp data and previous timestamp hidden state data as input. So xt is current timestamp data and ht minus 1 is previous timestamps hidden state data in this image. So this forget get determines how much to forget from past timestamp. Then we have remember get. Remember get also takes current timestamps data as input and previous timestamps hidden state information as input. This remember get determines how much to remember from present timestamp. Then comes the intermediate cell state, which also takes current timestamp data and previous timestamps hidden state data as input. Remember get is applied on top of this intermediate cell state. Now, when we once we have these components, once we have this forget get, remember get, and intermediate cell state, then actual cell state is calculated. If we look at the formula here, Ct is equals to ft times Ct minus 1 plus it times C tilde t. Here ft is the forget get, it is the remember get, C tilde t is intermediate cell state, and Ct minus 1 is previous timestamp cell state. Now we have hidden state and output state as well, similarly how we had them in RNNs. Now hidden state passes internal information to the next timestamp, and output state is used to produce output in each step. With the help of these components, LSTM handles the difficulties in RNNs. If we look at this formula again, if we set the forget gate to 1, empty to 1, and remember gate to 0, IT to 0, then CT becomes CT minus 1. This way, if we need some information to pass from first timestamp to the last timestamp, this cell state can be used. Now, this cell state is acting like a highway in this case. Now, there are variations in LSTM architectures as per the requirement. In bidirectional LSTM, information passes in both forward and backward direction. Some architectures are there which use p-fold connections, where input gate, forget, and output unit take cell state input as well as input. Now we also have GRUs, or gated recurrent units, where we have no separate forget or remember gate. We have a single update gate, and that update gate and 1 minus update gate becomes the remember gate and forget gate. There are some drawbacks as well in LSTMs. Due to backpropagation with time and gate calculations, LSTM processing is very slow. BiLSTM is even slower than that. Though very complex in nature, LSTM fails to understand natural language contexts in many cases. So, as advanced methods, attention mechanism, self-attention, multi-head attention, this kind of mechanisms are used nowadays. In most of the sequence-to-sequence tasks, we use transformer-based architectures as state-of-the-art. So these are all about LSTMs. Stay tuned for the next Sigmoid Tech Talk. Thank you so much.